Okay, so the expected configuration for chromium would be AR, 4s2, 3d4. That's what you should have. Okay. Copper, you'd have AR, 4s2, 3d9. And then silver is Kr, 5s2, 4d9. You have a smiley face for each that you got correct. I forgot to say this, I normally check like the questions you guys post first period, but the internet's been wonky today, so I didn't get to. Does anyone have a question about electron configurations from last time or the reading before we take the next step? Yeah, Evan.
How would you label like a noble like gas? Like how would you label argon?
Okay, so you can shortcut it with the one above.
Okay.
So you would do like neon, 3s2, 3p6.
Okay.
Does that make sense?
Yeah.
Good question. Any other questions? Okay, now, this is what we expect. But what happens is scientists have found a way experimentally to prove configurations. We're going to learn about it today. It's known as photoelectron spectroscopy, a lab technique. And once they figured that out, they found that for some elements, this isn't what it was. When they actually did the experiment, they found that chromium actually is this, 4s1, 3d5. Now, the AP curriculum states you do not need to memorize the exceptions of the configurations. But given an exception, you should be able to provide a reason why it's happening. Okay, so as we go through the exceptions, don't think, oh my gosh, you have to memorize these. You don't, but we do need to understand the why. So the whole thing here is it deals a lot with the proximity of the 4s and the 3d. Okay, when we're visualizing our little atom here, right, once again, this is quite wrong, but gives us something to stare at, okay? The distance between the 4s and the 3d is very, very close. They're very close in distance to each other because they're overlapping, okay? And what scientists have discovered is that when orbitals are either half-filled or all the way filled, all filled, that's a weird word, but oh well, it's not really a word, but okay, when one of these two things happen, it makes the atom a little bit more stable. Now, what we mean by this is think about the orbital diagrams that we drew last time. If I were to draw this out, this configuration results in something like that, while before, right, this one was like that. So what scientists propose is they propose that the atom uses, it's not much, but a little bit of energy to move the electron here, resulting in a completely half-filled D shell. And technically, the S is also now half-filled. Any guesses of why a half-filled orbital is a little bit more stable? Any thoughts? Yeah, Kimberly.
So electrons repel each other, so if you just have one in there, it's not repelling a different electron?
Very good. Yep, it's all about the propulsion, right? And that it makes it a little bit more stable because they're not having to push, you're taking that away from them. So, but once again, if this jump was too high, the atom wouldn't be able to do that on its own. It would need added energy to do it. Okay? All right, let's look at the next exception. So copper, when tested, actually has this. Ar4s1, 3d10. Turn to your table, buddy, and talk about why, possibly, this is happening versus this? Ready, set, go.
It's filling all of the spots up.
Okay, anyone want to volunteer their table buddy for a good answer? You're giving them a smiley face, so don't think of it as you're being mean to them. You're actually being very nice. Okay, Winston, you're being volunteered. He raised his hand first, but you did try to volunteer each other. Okay, Winston, why do you think this happens?
Because then it fills the D shell, and so D shell is more stable, and it also makes the F shell stable because they're not.
Yeah, so we have this combination of now we have half and full. When before we have full and awkward, right? Almost full, right? Good, Winston, have a smiley face for that. Questions on this? Okay, let's see if you're catching on to the pattern. Now, all of you on your paper, tell me what you think the expected, or the actual, I should say, configuration for silver would be based off these patterns. What do you think silver does? Fill that in on your paper. And then if you wrote KR 5S1 4D10, you can have a smiley face. You're correct. And that means you're catching on to the pattern of the exceptions of what they would do. Now, do make note, once again, that like for, let's say chlorine, okay? So chlorine's configuration is Ne 3S2, 3P5. The difference between the 3S and the 3P is too much for it to try to do that like these ones can. It takes more energy in order for that to happen, which it can happen, we'll talk about here in a second, but on its own, it can't ever do that, so it just stays in that orbital configuration. So, any other questions about the exceptions?
Those the only ones, or is there more?
Oh, great question. Let's do this. You tell me. Do you think there's another one that does an exception?
42.
Why?
Because it's like in the same spot as chromium. And
Yeah.
you have same amount of
Yeah, perfect. Zach, how does my face look? Yep. So molybdenum would also do a very similar thing that chromium did. Good. Any others? Isaac?
Could it jump to like the F? Could like the S jump to the F group if it was to like the middle?
So we do get some more exceptions down with the S as well. We don't really ever deal with these, so you probably won't ever see it, but we do find exceptions happen here once again because the orbitals get so close together again. So yep, no, great observation. Any other ones someone want to throw out for a smiley face that does an exception? Claire?
Would gold count?
Good, yep, gold does the exception because once again it's kind of in that same, we're seeing the pattern of the columns, right, where all three of them do that thing of moving it up. So good, that's my face for that as well. Okay, let's now talk about the difference between a ground state configuration versus what's called an excited state configuration. Okay, a ground state configuration is when the electrons are in their lowest possible orbitals. Okay? Right? They're on the ground. It's as low as it can go. Pretty much something in its ground state is following the rules as we would expect. An excited state electron configuration is when the electrons take in energy and move to a higher orbital. Or in a sense, we'll see skips in the pattern. Would be classified as an excited state. So we'll use oxygen as our example here. So oxygen's ground state is just going to be the 1s2, 2s2, 2p4. Right, just following the pattern for oxygen. An excited configuration for oxygen would look maybe something like this. 1s2, 2s1, 2p5. Where this electron, right, has been jumped up to a higher energy level. We get a skip in the pattern. Now note, this only happens because they're taking in energy. Right? They can't happen on their own, like we said, because that's too big of a jump. By energy, this could be like heat. If you heat it enough, you can make this happen. Electricity works really, really well to do this. If you send electricity through a sample, you can get their electrons to jump up. The thing about an excited state, though, is it doesn't stay this way forever, especially if you take the energy away. As soon as you take the energy away, the electron will fall back to its ground state. In that process of actually falling back, though, it releases the energy. And that's literally how we get lights. Is the light we get from the ceiling is mostly, it's kind of a blend, but a lot of times it's xenon in white lights. So the element xenon. Is the electricity flows through the xenon atoms, the electrons jump up. As they fall, they emit the light that we get. Of course, as soon as I cut off the electricity, well, they stop emitting that light because the electrons are back in their ground state. Questions on the difference there? Yeah?
How do we get like lights to be continually like the same amount of light then? If there's like electrons jumping and stuff, how do we get it to be like a solid light like these ones?
Yeah, so that's what's interesting is it's the difference in scale, right, between us and the size of like atoms, right? So it's like what we see versus what's happening at the molecular level. Because they are so small compared to us and it's happening so quick, to us it appears continuous. But actually at the molecular level it's not. They're actually flashing. Like it's not a continuous stream like we see. So yeah, great question. Kind of like somewhat analogous to like a fan idea, right? How like when a fan is spinning, it just looks continuous. But if you stop it, you can actually see the different blades. So yeah, Max.
Is that why with like some lights that are like kind of older, then when you take like a slow motion, then they look like they're flashing?
As far as I understand, yeah, that you can, with the especially the technology we have nowadays, right, you can get that pause that our eyes just blend into one. So yeah, great connection. Any other questions on that? Okay, third electron configuration type is known as an ion configuration. An ion, by definition, means that the atom has lost or gained electrons. Okay? So that's kind of when we use this word ion, it means we're losing or gaining. So keep in mind, we're not just talking about moving it up, we're actually talking about literally removing it from the atom or giving it new ones. Okay? So, for example, an ion configuration shows electrons that are added or removed from an atom, and it's normally because of due to bonding, which we'll get to next time, talking more about bonding. But in bonding, when chemicals bond with each other, those electrons are moving. They're either losing them or gaining them, is typically how it happens, or sharing them. Now, ions are always charged because what's the charge of an electron? Negative. So if you lose negatives or you gain negatives, it's going to change your charge. So how many electrons does oxygen normally have? 8, right? It normally has 8, and it also has 8 protons, which makes it neutral. But if it changes and gains 2 more, we would write it as O2 minus. So a charge indicates that movement of electrons. Negative charge means that it's gained electrons. You got to think a little backwards here because it feels a little backwards at first. You're gaining electrons, but you're becoming negative because they are negative themselves. Versus, like, let's say aluminum. If aluminum were to lose electrons, it actually becomes positive because you're losing something negative, right? It's like a double negative, right? If you lose a negative in math, you become positive. Okay? So what this means is oxygen now has 2 more electrons than it normally would. So its configuration would change and become 1s2, 2s2, 2p6. We add in those extra electrons. Right, so they get placed in the empty shell. Okay, try this one with your table buddy. Write me the configuration for aluminum 3+. Ready, go. You're always allowed to shortcut. What does that mean? You're off to the right start. Sure.
Where's it one?
Can't write it like that, but you are right. But you are right in your block. Well, they're gone, right? So can I write that for a configuration?
So I'd say you get rid of, then you know you have to get
What does it mean about this configuration? So when aluminum loses 3 electrons, it has that same configuration as the It's not neon. Well, technically you can't just put it in, you have to go to the one before and write it out too.
Oh, doesn't.
That makes
Oh,
sense.
yeah, no, I see.
Kind of like if you were to write a configuration for neon, you can't just put any brackets, right? You have to do HE. So your shortcut kind of didn't help you here. Is that you're having to like rewrite it, but logic-wise, you're totally right. Okay. I think everyone's there. I kind of walked around and saw. Those that aren't are there. They're just writing it out. So you should have, you can your answer a few ways, but you should have 1s2, 2s2, 2p6.
It's the same as oxygen.
Hey, look at that.
Hey.
Wins.
No way.
So, Winston, I don't remember, do you remember how you just phrased your question you asked me? Because I liked how you said it, but now I can't remember. Or your observation. What did you notice about aluminum?
That when you take it away, it's just neon.
Yeah. So I noticed there's a few ways you can write ion configurations. A lot of you wrote out aluminums and then you took them away, and in doing so you landed right on neon. You also could take them away to start with and see where it lands. But this right here, these two things are known as isoelectronic series of each other. They have the exact same electron configuration. Now, does this mean these two things just turned into neon?
No.
Good. What would you have to change to turn into neon?
Proton.
Very good. Protons, right? They're not neon, but they have the stability of neon now. Claire, do you have a question?
Yeah, I was gonna say, would the elements just be unstable?
Like,
Because of the
Charge
different
oxygen with enough
charges
atoms to make
or
it uranium
the different number of electrons?
like would this be unstable?
Yeah.
Great question. It actually is more stable. So next time or the next time, we'll talk about that when electrons get a configuration like a noble gas, they actually become very stable. And that's why why scientists name them the noble gases is because already those ones are stable. So we'll actually, you'll never see a noble gas become an ion. They never lose electrons, they never gain electrons. They like the way they are. And all the other elements on the table strive to be like them. They're like the cool kids. Okay, like that song, right? Great question, Claire. Yeah, Kimberly.
So would neon be included in this isoelectronic series?
Yes, so an isoelectronic series could have tons. What else could I include?
Oh, jeez.
You got it. What else would have the same configuration as neon?
So if you took away, noble gases are never ions, right?
Uh-huh.
So you could do if you did fluorine and then okay.
You got it.
Okay, so if you took away an ion from fluorine,
Close.
added an ion.
So it's going to be a negative charge. Maybe that's what you meant by. But this is also part of the electronic series, right? Because if fluorine gains one more, it's also like neon.
So what information do we get from knowing that they're the same series? Because almost anything can be added.
Technically, theoretically, yes. Actuality, no. Because what we'll find is certain things don't ever exist. Like certain things, like chlorine is not going to lose 7 electrons and become like neon. It just doesn't happen. So it is actually a smaller group than what it seems like. It seems like it could be infinite, right? But yeah, great question.
Could
Yeah.
you supercharge just like an oxygen and make it like an AR rather than like an NE? Or would that not work?
Yeah, so and once again, there's a difference in theoretical in chemistry, right, versus actuality. And the theoretical side of chemistry, I'm always I don't know. In a lab setting, if you're controlling things, could you force oxygen to take on that many electrons? Maybe. But in life, would it actually do that? No. But once again, in a controlled lab setting, could you make it happen? Maybe. But once they get to a configuration, so once oxygen were to get to neon, it's very resistant to change to anything else, right? Because it's already obtained kind of that stable state.
So, okay, that makes sense.
So, yeah, great question though.
So would it just go to its nearest noble gas?
Yes. So that will be the catch with learning about ions, is the ion it typically forms just takes it to the nearest noble gas. Yep, very good. Yeah. Any other questions on that?
Oh.
Mina just had a light bulb turn on in her head. I love it. Do you want to share?
Well, I didn't know that it went to its nearest noble gas.
Oh, cool. No, I love it. That's one of my favorite things of teaching is when, most of the time it's not an audible light bulb like yours was, but most of the time I can just see it on people's faces when it's like, oh, that makes sense now. So, okay, any other questions about electron configuration? Before we learn about the science that actually proves these things are real. Okay, while I get this pulled up, everyone stand up, take a stretch break, turn to someone around you and tell them 3 things you're grateful for today. Go.
Fruit snacks.
I'm grateful for
Minesweeper.
I'm grateful for technology. That's having it big, like for the school Wi-Fi and stuff is really hard. And then I am grateful for
Sometimes. Not all the time.
Kai, what are you grateful for today? Because you're missing your buddy. Okay, 1. Okay. Go away for now. Okay, photoelectron spectroscopy. This is a lab technique that they use to actually prove or know that these things of electron configurations exist, and it's not just something that they made up. Okay? Oh, before we get to this, I have a question actually for you. I'm going to hand you a little tiny piece of paper to write your answer down, actually. Because there's a lot of power sometimes in putting our words on paper, especially in AP chemistry where that's half the test, is we have to write it out. It's not multiple. Okay, put your name on this little slip of paper for me. Yes. Yeah, you'll turn this into me after because I want to just kind of read what you thought. Okay. If I have a positive thing and a negative thing, what happened? What do they experience? That's a horrible question. Positive and negative things do what? They attract, right? Okay, so when you have something positive and you have something negative, they're going to be attracted to each other. Now, scientifically, that force of attraction is affected by 2 factors. And I want to kind of pose it to you in a different way, because I want you to just, once again, recognize that things in chemistry are actually very, very logical in why they happen. And if you can understand the logic behind them, it takes away all the memorizing, because it's just, oh, that makes sense. Okay? So write down your name and then write question number 1. You don't have to write the question itself, just tell me your answer. So if I have 3, column A, B, and C, okay? If I were to measure the force of attraction between this positive and that negative for each of these, tell me which one do you think would experience the greatest force of attraction and why? So that's question number 1. Oh, you need a little paper? So pick A, B, or C. Which one would experience the greatest force of attraction? So if I were to measure it, and why? So I should see on your paper A, B, or C, and a Y. Once again, Y's can always be short, but make sure they are clear and a complete sentence. Okay, because we're practicing for how we would write it on an AP test. Okay, question 2 is the same question, but I'm going to draw a different set of things to compare. Okay, so comparing D, E, and F, which one is going to have the greatest force of attraction and why? Question 2, which one has the greatest force of attraction between D, E, and F, and why? Set your pencil down when you're done. Okay, turn to your table, buddy, and each take a turn sharing what you wrote. Ready, go.
So for question because the positives are like
The positives would be like where like I don't know, like since because the positives would roll a negative. I said D because it's stronger with magnets. If you have like magnets that are just hard words, they'll be able to pull each other as well. Or like you're gonna be as attracted. And if you have magnets that are like this, yeah, then they'll attract it higher. So
All right. Oh, got a few more. Sorry. Finish that. Okay. Thank you. Thank you for participating. I know sometimes it can be hard when you're like, I don't know if this is right. But once again, it's so much better just to get your brain thinking, even if it goes in the wrong direction. Because by going in the wrong direction, it does more to your brain than just waiting for me to tell you what the answer is and then getting it back in the right direction, right? Don't be afraid to be wrong. Don't be afraid to fail, because there's so much more learning that comes from it, okay? All right, show me using sign language. This is an A, this is a B, this is a C. What did you put for question 1 as the one with the greatest attractive force?
I'll go immediately if I look around the room.
That's what happens. Okay, the correct answer is C. C would have the greatest attractive force. Anyone want to volunteer their logic of why? Yeah, Max.
I just figured, I know that things that have more mass pull more, they have a greater attraction, and so I thought that maybe since there were more positives, then they'd be pulling like 3 times as much logically as like on the same.
Perfect, yeah. Right? This one has more positive force, so if you think of magnets, right? If you have more magnets, positive magnets, they're going to have a greater pull on that negative one. Yeah, perfect. Exactly. I mean, once again, does that feel logical? Like, that makes sense. Evan, I heard you say something interesting that's not bad. What were you were talking about this one right here.
Yeah, I was was thinking at first A because it would be like balanced, and I thought that like if it were C, all the positives would like separate and then attract on like different sides, but it'd still be like a stronger pole. So
But
there's
that
more.
was a genius thought, because technically, what would two positive things do if they were next to each other? They're going to push away, right? And it wasn't like, I mean, that really, like, you're looking outside of what's even being presented, and you're totally right. Minus the fact that we are talking about a nucleus. But what happens is inside that nucleus, there are other forces that hold the atoms together. But you brought up something that scientists wondered for a long time of, how does the nucleus even stay together, right? Why don't the protons just push each other away, right? So no, not a bad thought at all. So, okay, show me. This is a D. This is an E. This is an F. Show me your vote for this one. Which one would have the greatest attractive force?
I don't remember what this.
Make it up to look like the letter you want it to.
Wait, which was D? This. Okay.
This is a D. Very good. Okay, why would D? Claire?
I kind of just thought of it like magnets. The farther away the magnets are, the less they're going to want to like attract.
Yeah.
But the closer they're going to attract.
And when you play with magnets, you can literally feel it, right? Like if you have two magnets close, you can feel them pulling towards each other. Or if you flip them, right, pushing against each other. The farther you move it away, the less and less it's going to feel, right? This idea of positive and negative forces is a huge theme in chemistry because atoms are based off of positive and negative forces. So it's something we're introducing now, but will be a theme through many of the things we cover. So it has a name, and we'll talk about its name, but really don't get lost up in its name. Just understand this concept. But the scientific law that describes this idea of positive and negative forces is known as Coulomb's law, or they're known as a Coulombic attraction. Is this idea that positive and negative things are attracted to each other, and that attractive force is factored by two things. It's factored by magnitude, magnitude meaning the more you have, the greater the force, and distance. The closer the distance, the greater the force. So whenever we're trying to understand positive and negative things, always take into account both of those things, distance and magnitude, okay? And this is kind of the idea of how a photoelectron spectroscopy works. Hi.
Hello.
Okay, so the idea of a photoelectron spectroscopy is that we are going to put energy, actually I'm going to leave that up for now, into an atom so much that we are going to literally rip the electrons off. Okay, so think of our atom here, okay? So these electrons are held onto the nucleus. But if you put so much energy in, you can literally get these to start flying off and shred an atom of all its electrons. That's what happens in a photoelectron spectroscopy, is we remove all of the electrons from an atom. All of them. Every single electron gets ripped off. Okay? It's used, by the way, the energy they use are X-rays. Beware though that X-rays are a broad range of things. Someone last period was like, wait, when I get X-rayed, are they ripping my electrons off? No. Okay, just like how radio waves have a lot of frequencies, right? X-rays also have a lot of frequencies that they can be. So, yeah, Max.
Just wondering, what would happen if you like moved in photoelectrons?
And ripped off all of your electrons.
Yeah, what would happen?
So samples that go into photoelectron spectroscopers, it turns them into plasma. So you would become plasma.
Sounds like some superhero kind of.
That's true. That could be a cool like comic book thing, huh? Yeah, Kimberly. Is it releasing radiation?
Well, I mean, like, you know how, like, if you're exposed to radiation, it would cause a lot of problems?
Mm-hmm.
Because it's ripping out the electrons?
It could. Yeah, I never thought of it that way. Of like, that's why they don't. Yeah, because that can, and then that causes. Yeah, it could. I never thought of that before. Yeah.
So how do they rip apart, like, a nucleus? Does it work the same way? Just more energy?
bit, I mean, in a sense, yes, more energy. Because ripping apart a nucleus, if you remember from last year, since you learned it, goes into, I mean, that's the process of fission, right? Of splitting an atom, which is what happens in a nuclear bomb. So obviously the energy is like a lot more to get there. But the concept is the same, where if you put enough in, you can cause it to rip apart.
So could any element cause like a bomb when you rip it apart?
Theoretically, yes.
What?
Some of them, though, are easier broken than others. So like some atoms, it would be, once again, this kind of goes into the theoretical versus actual. So theoretically, yeah, any atom could split. But to get atoms to split, besides certain ones, would be really, really hard. It's already hard enough to split those ones, right? But to split any atom, because they just hold on so tight. There's like a force inside the nucleus, the nuclear binding energy, that would be very, very hard to disrupt in some of the atoms. But yeah, that's why like uranium does a good job at splitting, which is why it's primarily used for nuclear bombs and things. But yeah, good question. Any other questions on that? Yeah, Claire.
Or like when you're talking about like the nuclear bomb, like which ones would be like easier to rip apart and like why?
So the bigger an atom is, the more unstable its nucleus naturally becomes. And the more unstable it naturally is, it doesn't take as much to get it to go. Which is why, once again, if you look at uranium, uranium is the last biggest naturally found element there is. And so it falls apart a lot easier than the small ones do. Plutonium, the man-made one, also does a fairly good job, but that's the one that's primarily used, is that uranium. So, good question. Any other question on that for now? Okay, so here's once again the basic idea. We send energy in, the electrons take that energy, and instead of just jumping and becoming excited, they literally jump off the atom itself, right? And it's all about this binding energy, okay? This is where they were able to prove electrons are not all created equal, is because when they started ripping them off, some of them took a lot of energy to rip off and others didn't take very much. So they knew, okay, there has to be a difference here of how these electrons are held on. The higher the binding energy, the conclusion was, the closer it must be to the nucleus, because it takes a lot of energy to pull it off. Right? The farther away they are, the easier it is to remove them. So the graphs that we get with photoelectron spectrums look something like this. Okay? Oh, I hit the wrong button. Okay, let's pay attention. First off, anytime you read a graph, any class, ACT primarily, first thing you should always look at are your axes, the x-axis and the y-axis. What are they telling me? So the y-axis is a photoelectron spectrum, tells us the relative number of electrons, meaning how many electrons were removed at that particular point of energy. Okay, so the y-axis, or the height of the peak, tells you the amount of electrons. The x-axis tells you the binding energy, or how much energy it took to pull that electron off. Okay? Now, does anyone notice something interesting about this y-axis here that's important to note?
That it's not labeled.
What do you mean it's not labeled?
Like there aren't numbers.
Oh, did I say y?
Oh, yeah.
I meant x. Something about the x-axis?
They go big and small.
Yes, it's reverse of how you typically would build a graph, right? Where this is high in binding energy, and these are very low in binding energy.
Oh, I get it.
Okay? So what does it mean if it has a lot of binding energy? What does that mean about these electrons?
Those are really close.
So they're the closest ones to the nucleus. So what's the very first orbital after the nucleus? Good. So this peak corresponds to the 1s orbital. What comes after the 1s orbital? So this peak would be the 2s orbital. What comes next? Now, someone by raise a hand, tell me why is peak A and peak B the same size and height? Claire?
So you have the same amount
6 because a 1s and a 2s hold the same number of electrons, right? They hold 2. So this height, this actually is good that you mentioned it, Taylor, because the y-axis doesn't say numbers, right? But we know based off configurations that the 2s can hold 2 electrons, which means, how many electrons do you think that one represents? 6, because it's like 3 times the size. So what is this spectrum for? It says it up here, but if you don't read, it's for neon, right?
Imagine reading.
I know, huh? Questions on that so far? Yeah.
So is it just saying that like the 2p is the easiest because it's like the most outside?
Yeah, it's the farthest away, right? So it experiences the least amount of force, so it doesn't take as much energy to remove them. Yeah. And it also shows, look, that these two are really close in energy, right? Which is why they labeled them both as the second energy level versus the one, right, which is a big distance away. So, okay, let's take a look at a few more. Okay, so this right here is the electron spectrum for lithium. Okay, now I picked this one in particular just because something flipped on us.
They changed the way the graph.
Yeah, the numbers on the bottom flipped where now it's going low to high. Most AP questions I found do this way, where it goes high to low. But I've seen spectrums that do it this way, so I wanted to throw them both on there because the biggest thing you should focus on is the binding energy. How do I know which is the inner peak? Or the 1s peak is always going to be the highest energy. So wherever the highest energy is, which in this case would be here, label that peak as the 1s peak. And then in this case, this would be the 2s peak. Now why this time is the 2s smaller than the 1s? Yeah, because it's lithium, and lithium only has 1 electron in the 2s, right? Because our configuration is 1s2, 2s1. Okay, so once again, the biggest things we're looking for is that the highest binding energy always corresponds to the 1s. And then you simply just build up from there. But this is how, once again, scientists were able to see those exceptions, right? When they analyzed copper, they saw, hey, wait, it only has 1 electron in its 4s, and it actually has 10 electrons in its 3d. So they saw it, and then they had to try to provide a reasoning of why that was. That lower binding energy are always the valence electrons, right? The valence electrons don't take as much energy to remove. Okay, let's have you try with your table buddy these 2 practice problems on your paper. Ready, set, go. Do both of them, by the way. 1 and 2. They're not really numbered on paper, but. And put your pencil down if you're done. Oh, pass your little blue slip papers in the middle for me. I just want to read over your answers just so I can get some vibes of how we're doing with our justifications. Okay, either using sign language or you can pick up your periodic table because it has an A, B, C, D. And if you rotate it, you can show me your vote. Make sense? Okay, show me your answer to this first question here. Which element is represented by the spectrum given? Show me your choice.
Oh, wait.
Okay, if you're showing me B, have a smiley face. You are correct. I tried to make them all different, Bryce, so people wouldn't be influenced by others. So that you could be holding it this way and someone else could be holding it this way, but you're actually showing me the same answer. I tried. I need to rewrite it though, all my letters are fading. Okay, let's look at the next one. Okay, show me your answer for this spectrum. Very good. If you're showing me a C, you are correct. You can also have a smiley face. Any questions about, by the way, the abbreviation for photoelectron spectroscopy is PES. Yeah, it's kind of a mouthful. Any questions about these spectrums? So this quiz on AP Classroom, everybody. So your only homework is on AP Classroom. So keep that in mind. There's nothing on Canvas. Okay, so this quiz is all about spectrums. So pretty much questions like this. And then 1.5 is about configurations. Primarily, it will bring up like exceptions and stuff like that. Yeah, Mina.
Did we have a quiz last time? It was like
Yes, but I told you you didn't have to do it. Because it was this 1.5 and we hadn't covered everything yet.
Because I tried logging on the easy classroom and it wouldn't let me know.
Oh, well, hopefully you can now. Hopefully it was just a theme. Let me know if you can. But yeah, you didn't have any that were due. If you got on and saw one, hopefully you didn't do it. So.
What do you mean?
Okay, that just reminded me. I forgot to say one thing about exceptions for configurations, actually. Sorry, this is what happens when you teach lessons back to back. You say something and then you forget. You gotta say it again. Okay, no questions on this though? Okay, well, it kind of relates to this in some way. Going back to ions, okay? Let's say if I had manganese, okay? So manganese configuration is normally Ar 4s2 3d5. Okay? And that is its configuration in its ground state. But if manganese becomes an ion, primarily it becomes a 2+ ion. 2+ meaning what is happening to it? It's going to lose 2 electrons. We get something interesting here once again with the S and the D. The 2 electrons that get removed, so we still have Ar, but the 2 electrons that get removed are the ones from the 4s. Just because. No, there's a reason, Zach. Any thoughts on that reasoning?
Science.
Isaac?
If we take away it from the 3D, it doesn't make it half full.
Oh, not a bad thought, because dealing with like the half and the like half filled versus all the way filled. That's not why, but not a bad thought because that dealt with other ones.
To get rid of.
Yeah, in terms of energy or distance, the 4s is farther away from the nucleus than the 3d is. So it's kind of interesting that we remove electrons almost in a different order than how we fill them up. So you fill the 4s and then the 3d, but if you start taking them back out, they come out of the 4s before they come out of the 3d. Yeah, Mina?
Does that apply to the other ones too? Like, if we would take out, does that,
So like any of the ones in that D range, yes. Yep, you'll always think of it just numerically here, right? Since 4 is bigger than 3, you take them out of there first. Once level 4 is empty, then we start taking out of level 3. So, does that answer your question? Yes, okay. Yeah, Evan.
So, if we were doing the F section, would that mean we take away 2 before that?
Yeah, so F would be really interesting, right? Because they would take away, like, I don't know, let's think of one, just for fun. Once again, they're kind of weird, but they don't happen. Let's do lead. PV. So like its normal configuration would be 6s2, 4f14, 5d10, 6p2. Okay? So if lead were to have a 2+ charge, which it sometimes does, which 2 electrons would get removed? So go to the highest number, so it'd be one of the 6s, but then what's higher, an S or a P? A P, so these ones would get removed. But this is cool, I never even thought of this before. Lead sometimes has a +4 charge. So then where do they get taken out of? Yeah. That actually, I've never even thought about before. That makes sense why it does +2 or +4.
Not +3.
But it doesn't ever do a +3. Yeah, lead never forms a +3 charge.
So weird.
That's cool. Could you make it have a +3 charge?
wait,
Yes.
what if lead had like a negative 4?
Say that one more time.
What if it had like a negative 4? Is that possible?
It doesn't, but I see where you're thinking because then it would fill it all the way up to radon, right?
Yeah.
Because then, yeah, you're 6, you do go to 6p6. But yeah, lead actually never does a negative charge. That's a good observation though, because it seems logical that it could. So, yeah. Does that make sense though? I just remember there's a few questions on the quiz that had that D shell in there with removing. So, okay. We have 4 minutes. Okay. Kimberly,
Can you give us a practice that's like that one?
you want to do it on your own?
Yeah.
Sure, we can do that. So like give you an ion and you have to write its configuration?
Yeah, but a weird one though that like you drop the S or something.
Okay. Let's do okay, write me the electron configuration for Z. Oh, I have 2. This one is another good tricky one. So write me the electron configuration for these 2 ions.
Wait, does silver that just mean they're taking away 1?
Yeah, so in chemistry, kind of like in math, you don't have to put the number 1. You can if you want to, but a plus sign means just a 1. Yeah, good clarification. Kimberly, you remember memorizing last year how we memorized the charges of like aluminum, zinc, and silver? This like explains why they're like that charge holds it. Like why silver is a +1 and why zinc is a +2.
I was thinking it was 2, like,
There we go.
You just shorten it. I can't shorten it. I feel like
Okay, you have that for zinc. You're good. Any questions on that one? Okay, ready? Silver. Let's see if I tricked any of you.
Miserable. Like imagine running around like no belly.
freaking silver.
The reason being is because it's a double trick because it's an exception to a normal rule, right? So remember, silver's normal configuration is 5s1, 4d10, and so that one electron empties the s. So. Yep. Okay, let me know if you have any questions. I didn't put time limits on the quizzes on purpose this time, so you can be accurate in your work and not just click buttons because you're running out of time.